So the three battery form factors that I think are most common are the prismatic, the cylindrical, and the pouch design.
Sure.
And so the cylindrical are like your typical AA, C battery, whatever. And the benefit something like that is that they can handle pressures and changes from charging and discharging, sort of just by nature of their cylindrical shape.
Right.
Whereas the prismatic cells and the pouch cells, you need to do something to sort of contain them and compress them. And so when you're designing a battery pack around the 18650 or different cylindrical cells like that, you don't have to do as much to contain them and squeeze them. You're just basically more securing them and thinking about the wiring, routing, and all those kinds of things.
Yep.
And in some cases, because you're working with smaller cells, you could design your individual packs to be whatever shape you want. So you could design custom packs. Let's say you're building a 48 volt 13S, type of configuration. Perhaps the packs that are going to be, as you go up one side of the boat and turn the other side, maybe you're going to have like a sort of triangular front pack because you have an odd number of packs. And then you would have an even number on either side. I mean, you can think about that in your layout and get that weight all the way forward or however you'd want to do that. And by building your own batteries out of all these individual cells, you've got a lot of flexibility there.
Yeah.
The downside to something like that, though, is that if you've got one cell that for some reason is having an issue, that one cell could sort of drain, and it could basically be pulling power from all the other cells in that one group, in that one module. And when you're talking about a BMS, and its job is to say, I'm trying to keep this overall battery safe. And if one of the cells, even though in this case the cell is consisting of several individual battery cells, but that one group, if that group starts to dip in voltage, then it will limit the power from all of the cells.
Sure,
so that's where getting good cells is critical anyway.
Yep.
There's definitely a big used market for lithium batteries out there. There's companies that sell, whether they're sort of, I don't know if rejects isn't the right word, but batteries that sort of failed in some quality check before they were installed in an electric vehicle, let's say, but they're new cells maybe, and in some cases they're pulled out of it from being in use, but they have, not so many cycles that they're still in pretty good shape. And then you can go the route of buying brand new cells.
Right.
And from brand new cells, you've got, just to sort of summarize it into maybe better known and more expensive reputable sellers, and then great deals, which sometimes can be great nightmares at the same time.
Yeah.
So I guess the bottom line with wherever you get your cells is know what those cells are capable of and not just what the marketing pamphlet says that they could or should be. Because any one cell or one group that is underperforming is going to cripple the rest of the pack. And a great example of that would be probably exemplified best in this 144 volt nominal pack that we're talking about. When you've got 48 cells in series for a pack like that, if one of those cells, because they're all individual prismatic cells, if just one of those cells is going bad, it will cripple the entire pack. And so that's a pretty massive battery.
Right.
But one cell goes bad and the whole boat is dead in the water.
Yeah.
So that's something, testing them is really good. And so when I say testing them, you want to basically test them with a load and to get a sense of capacity. And ideally, you would test every single battery that you want to include in your pack to know that they're all pretty well matched.
Sure. I think the teams have had some experience, just return what you're saying about the reputable versus the not reputable, where they've bought batteries from a certain supplier, gone back 3 months later to get two more, and then all of a sudden it shows up and it looks different. And it has the same specs, but it's clearly coming from a different factory. And I think like having a little bit of overage, if you're going to put some larger car battery type batteries as like the baseline of what but having 50% too many so that when you start to find one that you don't like as much, you can get out of there. So one of the teams got the 18650s, got them, but then the university wouldn't allow them to weld them in their space because the aluminum welding had to be done by a professional, and they eventually found a way to get the work done, but it actually created like a pretty big unforeseen challenge in their Gantt chart.
I could see that would be
So I
big
think
hurdle.
that and like integrating the BMS could also present some of those similar challenges. So like if a team is considering whether to go with individual cells and creating their packs, like what kind of like local resources or university provided materials do they really need to have available to them?
Good point. So if you're going to be spot welding with 18650s, then you're going to need to have some spot welding equipment. And you can get less expensive sort of like pen type shaped things that, that I've seen people use them that they seem to work pretty well. The sort of more consistently operating modules that I've seen, and I can bring up on the screen to show, but
Sure.
we've got a box that basically has some electrodes that come out, and when you press up into them, it hits a reed switch and it sends the power through short copper studs that do the spot welding, and you could adjust the number of pulses and the amount of current, and you can fine tune all that stuff. And the reason that's something where it does take some experience to sort of do some testing, ideally maybe with like an old reject cell that maybe doesn't even have any power in it, just because you want to know for sure that you're not going to overpower it or do something that is going to damage the cell. So one of the things that I've seen happen with spot welding, if you really cram way too much power into a cell, is I've seen it where it literally will pop a hole through the shell itself, and it will make an opening where it will vent out. It will either drip out or it will vent out, depending on what happened inside.
Right.
And so that's where having a cell that is just an old spare cell that has no life, has no charge to it, is probably a good idea to do some testing to see what settings are ideal to get good weld, penetration and everything, but you don't want to blow holes through the cell,
Right.
And through the tabs and everything. So testing of that all out with sort of some scrap things is a great idea. The other thing that we found, and this is one of the things when our students were spot welding together, I guess it was about a 5 kilowatt pack. That was a 48 volt pack in a couple of versions ago of our batteries. And one of the things that we did was the students, we gave them an overview of all the things to be doing, but we also didn't necessarily sort of say, feel free to experiment with the settings and see what happens,
Right.
So from an advisor standpoint, I kind of knew in advance where the tolerance of where I would want them to be operating was. And then, I basically said, feel free to adjust as I'm there overseeing the process, and I would catch them before they would try something. Not that had happened, but I was ready to say, you're going to go too high if you continue to increase whatever, kind of a thing. Because you want to let them have the hands-on experience, but at the same time, you want to make sure that they're not going to have a problem. And lithium batteries are one of those things. I remember when we first started buying lithium batteries from a supplier, and we were talking about building packs, and this was probably early enough that it wasn't as common, that people weren't doing this on their own as much. One of the things he said was, just be aware that when things go south, and if you get a short circuit and you get a fire, you're not going to be able to put it out. And it's not going to be a matter of getting a fire extinguisher or whatever. By the time you realize you've got a problem, you've already got a significant fire.
Right.
So part of what we did to sort of be working in a safer process is, so we had a 13S battery pack, and each of those, in this particular one, I think it had about 45 18650 cells. We had the students first would create a strip, and we had a certain size strip, like let's 7 or 8 or whatever it was. So they would just all be in parallel, and they would spot weld those all together. And so there's not a ton of energy in that. So it's a little safer. You're also not increasing the voltage. There's not ability as much to sort of accidentally have two terminals that are side by side, that in the process of shorting across them, you now have a complete short circuit. And so that was one of the things that we did. And then they would take these rows, join them together, and then cross them, with the other, nickel strips, spot welding them, still all in parallel. So they would build these large all parallel packs. And then from that point, it was a much more, from a safety standpoint, I'm going to explain what I'm doing, and I'm going to be the one that's connecting them together, so that way we don't have in our library where we were working, full of all the books and everything. We're not going to be sort of building without the sort of experience at the helm, putting together this 48 volt pack with 5 kilowatt hours of power stored in there. That could be obviously a problem. And so, but by making each of these modules the way we did, we never connected them together, and we never spot welded them together to make that process less. I didn't want to take that away from them. So
Right.
what we ended up doing was we made these individual modules, and then each of them had I guess it was maybe a 6 or 4 gauge wire that came out of it, crimped on a ring terminal, and then each of those would either connect to the adjacent ring terminal of the other battery, or a nice big bus bar to jump from the next group. So that way, we assembled it outside of the library, where our makerspace is, on site. And made that bigger pack.
Sure.
So, but if you're going to be building a pack where it is all spot welded together, it all in a contained, battery, where the result is all of that higher voltage battery ready to be discharged if something goes wrong, then just be safe about doing that. I guess one of the things to maybe point out, it may be obvious in hindsight, but for new people, the casing of the cylindrical cells is all part of the anode or the cathode.
Right.
And the sort of the negative side is essentially all of the shell, and only the center of the top of the cell is the positive terminal. And so the perimeter of the top of the cell is part of that negative terminal. And so if in the process of spot welding together, you spot weld the end of the cell, but the wrong part of that end of the cell, you could easily make that short circuit.
Sure.
So be ultra careful that when you're putting your nickel strips across, that you're not accidentally setting the spot weld into that perimeter of the battery itself. And ideally, you would have the little ring sort of insulating material there to sort of separate that. But again, it's who knows how cells are from different suppliers, different manufacturers may be different. So just be super, super careful with that.
So let's go back and pick up the bus bars.
Yes.
What's their role, and what do they afford when you're designing an electric system?
So you're going to have all these individual cells, whether a cell consists of several 18650s or cylindrical cells, or whether it's a single large prismatic cell. Each of those cells has to be connected in series to make your eventual battery pack. And to connect them all together, bus bars are a pretty common way to do that. And so as opposed to, let's say you could use a short length of heavy gauge, whatever, battery cable with terminals on either end. The good thing about bus bars is, one of the things I love about them is, first of all, the simplicity if you've got a battery that works well with bus bars. So like the big cylindrical lithium iron phosphate, the big prismatic lithium iron phosphate batteries with the upright posts that you can bolt, it's so easy to make a battery pack out of them because you just line them all up and you just sort of drop them in, alternating, back and forth to connect from one to the next. And it's super easy to make a great, consistently, connected battery, pretty safe to be working with. When you're making all of your own battery cables, let's say, you've added another layer of complexity of how well did I crimp that connection on there, and is there any chance that it's going to pop loose?
Right.
And the ring terminal stays where it's supposed to go, but now you've got this length of cable that might wiggle around and short circuit or whatever. But the other side of it is, there's an art definitely to getting really good crimps anyway, and this is something I'll go into later, talking about different kinds of cable, the crimping methods, and all the things that are involved in that. But I guess my point is that if you can get good bus bars, they're all pretty much identical. And the advantage to that is that you've got a consistent connection with good high current transmission for the power, and the resistance from one connection to the other should be pretty consistent as well. And if you've got, let's say, for example, sometimes if people are, this is one of the things, I'm not trying to say that I'll tell you how we've always done everything right. It's a lot of stuff we've learned along the way. And so early on, I was under the impression that soldering those kinds of connections was going to give you a better connection, because you would have a sort of more solid connection there. You wouldn't be relying on the sort of physical crushing down between the terminal and the wire. And my thought process was, you'll be more likely to get corrosion inside of that connection over time. You'll have a worse, you'll have more resistance in the connection. And by soldering that, I assumed that would be the ultimate, because you've made this really good solid connection. It's electrically connecting it. But what I didn't realize at the time is that the solder itself doesn't conduct as well as the other materials are, the copper,
Sure.
or if it's going to be, the nickel, coated wire, or, the nickel coated copper for the bus bars or whatever. So, if you're talking about using a solder, then you're automatically going to have this pinch point electrically where you're going to have heat that's being generated. You're not going to have consistent, if you don't solder them all up exactly the same way, if you have one that has a little bit more solder in the joints and things like that, you'll find that you're not going to get the exact same level of resistance through the bus bar. And that makes a bigger difference when the BMS is trying to look with accuracy at the cell voltages amongst all these different cells. And if you are sensing a voltage drop, not because the battery is actually dropping, but because something about that connection isn't giving you the full story about that, the battery's status,
Sure.
then it might cut the battery sooner than it needs to. Or if it's trying to do some balancing, it might be pulling power and putting it where it doesn't need to go because it thinks a battery is a little lower than it really is, but it's really just because you've got this inconsistency with all your connections.
Right, right.
So
and I think one thing that teams always ask me is like, how could we lose or how could we win, right?
Mm-hmm.
And I think the two things that you were just speaking about is how we see teams that could win lose. It's the crimping in the connections and the soldering. That these things, they seem like, we're engineering, we have clean sheet, we're working on these, but then like the actual hands-on materials end up being the thing that allows electricity to flow through at hopefully a low friction rate, so that way it can get to the end as quickly as possible.
Yeah, and I can add some additional videos to sort of show more nuances of all the fine details of that. But when we're talking about bus bars, generally if you buy, let's say, prismatic cells, the supplier will most of the time supply them with the hardware to connect one to the next.
Right.
And I can go into more detail again in a separate video about the terminal types, because there is something to be said about that as well. But generally, if you've got a good supplier, the bus bars are well matched to the batteries. So if you've got a 280 amp hour lithium iron phosphate cell, then a 1C discharge rate, the bus bars should be able to, in theory, handle that. Now, realistically, there's a whole second, I guess, another debate, which we probably shouldn't get into a ton here, but when we're talking about the sort of EV grade versions of these cells and what we think of as being like the A grade version of the cells, realistically, the best of the best cells aren't really ever available to us as consumers. Okay. They're first available to the auto manufacturers, who are the ones that sort of had these initially built for them. And so we're kind of fighting over the best of the seconds. And so that's when you get into the A grade, B grade, or that whole discussion. Generally, we're already talking about those seconds, which still can perform very well.
Right.
But when you're talking about, let's say, for example, a prismatic battery that you're building into an electric vehicle that's being mass manufactured, all of those connections are all laser welded together. And so it's under those conditions that you're going to be getting the 1C discharge, and everything is capable of what the data sheet says.
Right.
But as soon as you add in a post as a sort of a post-processing process, as soon as you add that terminal to it, then you might find that you've just reduced the actual surface area of the terminal, that it may not be truly able to carry a 1C, in the case of that size battery, 280 amp continuous current without getting hotter than is normal. I'd say for most people that hasn't been a concern that I've seen. Most people aren't drawing that much power. But I shouldn't say that, because there are some boats that are going pretty fast out there, and I don't really know how close they're coming to the limits of a cell like that. So.